Microsoft Research in Cambridge, and I'm here to tell you about the Confidential Consortium Framework, which is our project. It only says on the last slide, which might have been a mistake, but it's open source on GitHub, so please feel free to check it out. So what we set out to do is build a framework to make it easy for people to construct multi-party applications with good guarantees. So one of the things that's often a problem is the lack of governance mechanism. So we wanted to have a verifiable consortium governance mechanism, a system where you can have very well-defined governance rules for the multi-party application, which are easily verifiable to all participants, to members themselves, and to also users, so they can see that the network is, or the application is run in a specific way that is promised it is to be run. We also want fine-grained confidentiality, of course, so people should be able to have very fine-grained control of their data. It should be possible for application makers to make it so that you can only see or reveal, what's useful and appropriate for business purposes. We want a very simple programming model. Everyone wants a simple programming model. We want it to be approachable and make it easy for people to get those guarantees. And of course, we want high availability and high efficiency. It's no good to have an easy framework if you then have to do a lot of legwork to make your app available and fast, right? So broadly speaking, from a faraway distance, this is what a CCF application looks like. You have a number of machines which run trusted execution environments or hardware enclaves running anywhere. So they could be running in a cloud provider, multiple cloud providers. Some of them could be on-premise. It doesn't really matter where. A bunch of users interact with that service. And the set of members basically provide governance. So the first thing they do is they endorse the service. They essentially endorse the identity of the service and make it so that everyone knows that this is the service they're talking to. They also govern the service, so they'll govern the membership sets. They allow new members to join or to leave. They can add and remove users and all that. And they'll look after upgrades too. So if they need to replace the code, improve the application, fix security bugs and so on, they're on the hook for that. Separate from them is an operator, someone who's just provisioning things. So they're providing the hardware. They can spin up the instances of the nodes that the application is running on, but they're not trusted. They're not inside the trust boundary. So they're spinning things up, and they can provide them to the members on behalf of the members. Maybe the members pay them to make this available to them, but they do not have any specific access to the application. They're not part of the trust boundary in the application. So how do we bootstrap that? How do we get that started? And for that, we need a number of trusted execution environments, and we need a way to sort of connect them together and make them into a coherent network. Sorry. Speak a little bit louder, please. Yes, I can try. Yes, sorry. So trusted execution environments, mostly everyone, except, well, that person left, but mostly everyone is familiar with them. So what we get is we want encrypted and integrity protected memory. So this is key to make sure that the operator, the person who's running the nodes on their machine, cannot have access or cannot see anything that's happening inside the node. We want cryptographic evidence over running code. So we want the ability to assert at the distance or to check at the distance what's running. And finally, and remote attestation. So we want to be able to do this remotely. And this gives us a distributed trusted computation. So it allows us to spin up a number of enclaves and to check that they are running in enclaves. So the contents or anything we send over to them or anything they contain is not immediately visible to the people who are running these enclaves. We want to be able to know exactly which code they're running. And then we can make them part of the networking. We can distribute our application with confidence that information is not going to be leaked or we're not going to have integrity issues or this sort of stuff. So how do we do that? So node overview, so a single CCF node roughly looks like this. You'd have a client talking to the node. They use TLS, so we don't support generic byte streams. We support only TLS. You have to talk to us via TLS. That goes through the host. The host is potentially malicious. They potentially can look at all of the frames and so on, but these are encrypted TLS frames on the way in and out, so they can't see anything useful. They can't derive anything useful from that traffic. They're no different from someone who could be intercepting some of the network traffic there. So the TLS session terminates inside our enclave, and inside our enclave is essentially 2 bits. There's our framework, which provides a certain amount of functionality, and the user application code, which is running whatever business logic there is there. So the enclave contains the application logic and states. It contains the governance code, which is what we referred to earlier, which is what allows these enclaves to talk to each other, and fault tolerance code, so code that allows us to distribute essentially the updates across the network and enclaves and make sure that we have availability. If a certain number of enclaves are affected or come down, the application still can run. So communication between the host and the enclave, we want to avoid e-calls and o-calls. So we want to avoid calling in and out of the enclave. There's a number of performance and security reasons why it's not such a good idea to do this on a regular basis. And you want to minimize the amount of this you do. So the way we do things is there's a single o-call at a single e-call at startup when we provision the enclave, and then all communication between the enclave and the host is done over ring buffers. So essentially, we put data on the ring buffer. The enclave reads it out on the other side, and then back in. I see a lot of people take pictures, and I want to point out the slides on the website. So you don't have to if you just want the slides. So yeah, the communication is basically just the TLS frames in and out over the ring buffers, and also heartbeats. So we'd like to have trusted time. There's no such thing as trusted time, but we still need some notion of time, because if we're going to run a distributed consensus, for example, we need something to do timeouts and this sort of stuff. So we take rough time from the host. It's not trusted, and the host could essentially perform a denial of service by withholding time updates or sending time updates too often and so on. While we claim this has no impact on confidentiality and integrity, basically.
Doesn't it have an impact on availability?
It does have an impact on availability. So if you want to perform a denial of service and you're the host, you certainly can. But then again, if you're the host, you can impact availability by withholding all TLS frames from the enclave, and then not much availability there. So yeah, for sure. So the way we do availability is you distribute this, and you have a number of enclaves running, set up with a consensus mechanism, and then so you have to take down, at least half the enclaves you're running CFT, maybe a third if you're running a BFT variant, right? But yeah, if you take down, or if you own all the hosts, then yeah, you can stop the system from working completely for sure. Yeah. So yeah, so now that we have these building blocks, we can talk a bit about like a join protocol. So if we have a network that's already established, that's already bootstrapped, so the way we start out is we start a single node, and then we gradually bootstrap the network by adding on new nodes to that network. So the way it works is our nodes create a key pair, very much like Jethro's scheme, so that stays inside the enclave. That's the identity of the enclave. And the node produces a quote over its states. So that's the platform, the code it's running, and the identity. So the platform contains platform information. It contains microcode version, that type of information as well. And then that's sent across to the network, and the network then decides if this node should be allowed to join or not. And there's basically two parts to that. One of it is checking the quotes, so making sure that the node that wants to join is in fact running. SGX is running the right microcode, is running everything's up to date, is running the right codes inside the enclave. And the other part is governance kicks in here. So essentially a proposal is created and it's put in our state, and then our governance mechanism, which I'll talk about just next, kicks in, and the members get to decide if they want to allow this node to join or not. In some configurations, you could decide to allow that all the time. So if you've got the right identity, you're running an SGX, you're running the right code and so on, maybe everybody's allowed to join. There's some reasons why you probably don't want to do that. Or maybe the members have set up some rules. Maybe they want to check who's joining first. Maybe they want to just check the quantity of how many things are joining at the same time. There's various problems with having too many joins at the same time. Obviously, everybody comes in, and then they have to catch up, and it creates a problem. And so the network, if it decides that it likes the node and it wants to add the node to its configuration, then endorses this identity and sends data secret, basically, to that node. So consensus can kick in, and we can start replicating state to this node, because now they can read the updates we send them. And so we have a single network identity, which is distinct from the identity of the first node, but is essentially set up by the first node. And this network identity is what would be distributed. So that can be, you can produce a CSR for that, have it be signed by root CA, or that could be something that the members distribute to their users. So if you think of the members as a group of companies, maybe a group of banks or something, they could distribute this root certificate to their users. And users can, when they connect to a node over TLS, the fact that the certificate for the node is endorsed by this root cert, this is how they get proof or evidence that the attestation has been conducted properly and the rules of governance have been followed properly. And so yeah, so once the node has joined, then it needs to catch up on state and become part of the system. So that leads us into governance. How do we build a mechanism to make it easy for members to decide how the network should be governed and operated? So we have our consortium of members, and initially, what they do is they endorse the first prefix of the ledger and the configuration. So we have a first few transactions that configure our system, and the members have to come in and they have to stage a vote basically to say, yes, we agree this is the network we think we want it to start. So it's running the right version of the code, it's running with the right membership, and we're happy with the identity of the node so far. So they vote for that. This is recorded. And in general, this is just an instance of our generic governance mechanism, which is staging votes. So you can stage votes to decide things like membership, who should be a member of the network, who should be a user, what the network configuration should look like. So I want to add a certain number of nodes, remove some nodes. I want to update the code, or I want to change the versions of the code that are allowed to run in the network. Or you want to change maybe the constitution itself. So all the votes are governed by a constitution, which is a script, which I'll show on the next slide. And this is what decides how the votes are passed, essentially how the votes are counted. And this itself, being part of our state, is something we could update also, probably with different rules. Maybe we want to be stricter about that. So the constitution is a script. The votes are scripts. So the proposals, are scripts, and the votes themselves are scripts. So a proposal could be, we want to make this change, and then all the members have to look at that, and they have to say, yeah, I agree or I disagree. But if you say I agree or I disagree, then you have a time of use problem, because things could have moved on. And maybe you care about some other elements of the state. Maybe you're happy to add a node, but only if there's not like more than 10 nodes already, because you're trying to restrict the total number of nodes. So in your vote should be something that's executable. It should be something that can look at the proposal, but also the current state of the system and say, yeah, okay, I agree with that. Or, given the circumstances, given the state we're in, I don't want to accept that. So because your vote is executable, you get rid of these concerns. And this is how we count things. So that's all the slides, and we should see a bit of code. Hopefully it's big enough for everyone to read. Okay. So I'll try and go through that quickly, but essentially this is a very simple constitution sample. Some of them will look bigger than that. They'll be more complicated. But here all we're doing is we're saying, look, for most things, all we're looking for is a majority of members saying that they agree. So if we want to stage a proposal and we want to say we want to add a new member, for example, or a new user, we just want to have a look at the majority of members which are currently active and check that they agree with that. So we count member votes, and essentially we just count member votes for active members. So if we have members who have been retired or who are joining and they're in the process of joining, they're not active yet and so on, they shouldn't be counted in this vote. We count all the members the same. We could decide to make a distinction. We could have some tables where we store special members who are like operating members or senior members or whatever, and maybe they have special rights. Maybe they can veto some things. Maybe their vote is sufficient to pass the entire thing. It's very flexible. We can do pretty much anything we want here. This is just a simple example. There are some tables where we store information that maybe shouldn't be so easy to modify. So for example, if the members want to stage a vote over, so there's a whitelist table, which is basically the tables that are allowed to be affected by governance. And then we have our governance script table, which is the table that stores this constitution. If people are going to replace the constitution, you're probably looking for something more than just a simple majority. So here in this case, we enforce unanimity. We need to have the total number of member votes needs to be the same as the total number of members that's active. And so if we have a majority otherwise, then we pass, otherwise we return false. And the way this works is very simple. Every time a member sends a vote, their script is executed that decides their vote. Then the constitution is run again. We count. If it's good, we pass. If it's not good, still pending. The proposal is still there. There's a way to withdraw proposals as well if you think there's no realistic chance of them passing. But that's sort of how it works.
The types of proposals are fixed because people need to write code to vote on those proposals.
The types of proposals are fixed. Not really. So because your proposal, so this is Lua. Your proposals are Lua and the votes are Lua. If you can put your proposal in terms of a Lua script that executes against the table in the key value store that's backing this, then you can put it to a vote. And the other members, they'll have to write a script that knows how to evaluate your proposal. And so it might be tricky for them if you propose something sufficiently complicated. Maybe they won't agree to it. Yeah, but.
So that's what I mean. At the moment where your proposal is submitted, you have already written code for it. So
When the proposal is yeah, your proposal is code, so yeah, you have to come up with. So conveniently, we'll look at proposals now. So some simple ones. The first one is just we want to add a new user. So we get to see the tables and Sorry, that's a mistake. It should say user cert. So we get the tables and the user cert as arguments here, and what we're saying is we want to add this new user to our store. So the way this is split is the proposals are typically little bits of code, and some arguments are templatized and parameterized. So here the user cert is passed separately, is passed in. So the next proposal is we're passing a new code digest, and we're saying we should be able to run this new code version in our system. And we can have a look at the ballot here, so a vote to evaluate that. So the vote to evaluate that will look at the changes proposed by the proposal. So it checks there's only one change proposed, that the proposal is a new code proposal, and that the new code is this new code ID that we have decided is acceptable. So probably typically what would happen is the member would have ahead of time communicated with the other members and say, hey, look, I want to deploy this new version of the code. I give you what you need to reproduce the build. You edit the code, you reproduce the build, you get to the same ID, you get the same hash over the code, and you decide, like, yeah, okay, I want to put a vote for that. So you're not accepting the proposal itself, you're accepting this particular code ID. That's what you're accepting there. Yeah, so code updates, it's essentially a sort of simple three-phase mechanism. You add a new supported code version through this vote mechanism. Everyone agrees to that. For a while, when you do that, as you spin up new nodes that run this new version of the code, you want to make sure that the new and the old versions are compatible. And then you can stage a vote to say, I want to remove the old version of the code. Now that we've upgraded, maybe the new version contained a security fix, and you don't want to allow the old version to run anymore. So you stage another vote to say, we should get rid of the old version now because we have a good quorum of nodes running the new version. And then if that passes, then the new vote, the old code is essentially removed, and so nodes that are running the old code can't be part of the network anymore, and now you can tear them down. So another thing we potentially need governance for is catastrophic recovery. So typically we run with a consensus algorithm, and there'll be a formula that tells us how many nodes we can tolerate are failing, and that's basically F. So if we're running CFT, crash fault tolerance, if we have two F+1 nodes, we can lose F nodes and still make progress. If we're running with Byzantine fault tolerance instead, we need to have three F+1 nodes, then we can tolerate F failures. Well, if we have more than F failures, then the network can't make progress anymore because there's no quorum, so transactions can't be globally committed, and now we're stuck. So in that case, we need to perform catastrophic recovery, and what happens is we need to go back to the members who are ultimately the root of trust for this. So we have a mechanism that uses key shares to do that. There's also an older mechanism that uses sealing keys, but essentially you need a way for the members to come together and put together enough information that they can read the old ledger and produce a new service that runs on the basis of the old ledger. And you want to have the new ledger endorsed by the old service. So if people are connected to your service and you have not distributed the new identity of the service to them yet, they can still connect and they still know that this is endorsed by the old identity. Here the members have quite a lot of power, so it's up to them not to endorse a new service or not to endorse multiple new services, for example, or to endorse a new service unless they're happy with the state of it. But it sort of works the same way as the bootstrapping the first time works. Someone stages, one of the members stages a recovery vote. The other members get to examine the state of the service, and if they're happy with the state of the service, then they endorse it and they can move forward. And so finally, we want verifiability. It's no good to have a well-defined governance if no one can audit it, because then there's no trust. You have to trust that the code has been written correctly and that all the votes have been executed correctly. So for that to happen, all the governance states, all the tables that hold the governance in our system are all public. So anyone who has access to a ledger, which should be anybody, can see what the governance tables hold, and they can essentially play through the governance story. And if anything doesn't match, like one of the votes, the total that was counted doesn't match and so on, they can say, hold on, there's a problem there. All the governance transactions have to be signed. This is enforced by the service as well. So you not only can say there's a problem there, you can also blame whoever is responsible for this, which are the members has basically made a mistake or lied about the way they voted, for example. This happens in the same total order as other transactions. So all our transactions happen on the same KV, and governance is done over a set of tables, which is part of this KV. They're not separate. So the versions, the commit IDs you get for governance changes and for regular transactions are on the same scale, on the same time scale. So it's very easy to decide which business transactions should have been affected by governance. So if a user, for example, has been kicked out of the system and you're trying to figure out exactly until when they could have performed transactions or they should have been able to perform transactions, you can easily because it's part of the same version timeline. And so finally, yeah, all of this is recorded in tamper-proof ledger. So we use sort of standard blockchain mechanisms or Merkle trees to make sure that all our updates are chained and that you can't just go back and edit some part of the history without it being very, very visible later on. So it's all good to have this stuff, but it has to be easy to write applications for it. So the first guarantee we want to make is that unless you really go out of your way to log like private information, all data in CCF is encrypted all the time. So it's obviously encrypted at rest. So all the data we have to store on disk for recovery and audit is encrypted. All data that is sent around the network is encrypted on the wire. And in memory, we also get encryption from our use of enclaves. So if somebody has access to the machine, they cannot just look at what we're doing. So roughly speaking, our application schema looks something like this. The application code plugs in the gray box, and everything else is provided by the framework. So client frames come from the host. That's just TLS. It comes to us as TLS frames. We have a front-end component that just takes care of essentially the TLS functionality, decrypting things. We have authentication against the KV. So remember, we know exactly at which point in time which users or which members are allowed to use the system because of our governance. So we can check that. And then if their identity is not allowed to do the operation they say what they want to do at this point, we can reject it automatically. It's not something that the user has to worry about. So things come to the user with this identity that's been verified. So we've authenticated transactions and we've also authorize them at this point. And then the application engine can just produce a set of read and write transactions or a single, read and write transaction against the key value store. So that in their business logic, all state has to go in the key value store that's provided by CCF. They can perform any operations they want, but in order for the state to be persisted to the ledger, to be recoverable, and to be distributed and available across the network, it has to happen as operations against the key value store. And then further downstream, we replicate this using consensus. So that again goes back out to the host. It's a bunch of encrypted frames back out to the ledger, so to be stored in permanent storage. And at the regular interval, we also we hash all the transactions. We put them in a Merkle tree, and at a regular interval, we sign that. That goes to our ledger. So this is how we get our tamper-proof audit log. So yeah, so we have encrypted TCP frames coming in and out of the ledger. That's sort of coming in and out, of the application. That's the only thing that goes in and out of the enclave. We have an append-only ledger on disk, and all application states must be in the key value store for all the guarantees to hold. So we have a couple of consensus variants. Crash fault tolerance is the main one we use now. We have a BFT implementation that's still kind of work in progress, but which is available in the build for people who want to try it. So if you use crash fault tolerance, we have an in-enclave raft variant. What we do there is if you have two F+1 nodes, you can have up to F failures, and the network will still continue to make progress. Because we've added signatures, you can blame compromised nodes, and you can essentially go back to the ledger and offline verify what has been done and potentially take things out if you think some nodes have been malicious, but it's not happening online. So if a node somewhere is acting maliciously, they can potentially go on doing it for some time. You have to offline check for that and remove the transactions they've done. And so here we rely on the T for both confidentiality and integrity. If the T is compromised, if someone can, for example, tamper with the memory, we won't be able to detect it online. It'll take some offline audit for it to be detected. If you use our PBFT variant, which again is still work in progress, but it's coming online, then if you have three F+1 nodes, you can tolerate up to F failures, but you can tolerate up to F nodes being malicious. So the nice thing about that here is that you still rely on the T for confidentiality. So if SGX is utterly broken one day, well, your data still is no longer confidential, but you potentially don't lose integrity if fewer than F nodes are affected. So if you're clever enough about the way you distribute your instances, and they're not all subject to the same attacker because maybe they're geographically distributed or distributed across multiple cloud providers and so on. If you manage to keep two F+1 nodes that aren't affected by the attack, you still keep integrity. So your attacker gets to see the data, but they don't get to manufacture transactions that are illegitimate. So the key value store is basically our very simple storage interface. There's really just two things you can do with it. You can get stuff out of it and put stuff back inside. Like the rest of CCF, it's implemented in C++, so we'll get to the runtimes that support it, but you can put any old C++ type in and out of there. And then for other languages, we have mappings. Transactions are very straightforward. It's like any local key value store we've used. We have strict serializability and opacity so that errors only see a consistent state. There's really no tricks there. It's very, very easy to use. It behaves the way you'd expect. You can have app-driven confidentiality because of this very flexible key value store model. So the app decides completely how it wants to expose data. It's up to the application logic to decide how to do that. There is no built-in support in the key value store to label things with certain degrees of privacy or anything like that. It's completely left to the code. And you can, of course, store your code in the store itself. So you have the key value store, and one of the things you can do is some of the values could be code themselves. So if you want to upload scripts, if you want to upload things that can be executed by the users, then of course you can. Another thing that the framework provides for you is transaction receipts. So this is a little tricky for you for the applications to implement themselves for a variety of reasons, but basically applications should be able to, or users that use the application should be able to get receipts from the application that are signed by the service that say that this outcome happened and it happened at this version inside the KV. So if you're talking to people who are outside the system and you're trying to prove to them that something did happen or you did do something and you want to give them cryptographic evidence that this thing happened, and it should be something that can be verified offline, they shouldn't need to be a user of that system and to talk to that system to verify that this happened. You can do that through the receipts. And so you can write your CCF apps either in C++ directly, which is probably what you do for maximum speed, although it's a bit tricky, but it's not that bad. It's modern C++. Or you can use one of the runtimes that we've built. So the standard one that's better tested that governance runs at the moment is Lua. We also have a project called EVM for CCF, which allows you to use any EVM compatible language like Solidity to run smart contracts against the KV store. Or recently we've added JavaScript support. It's still a bit experimental, and there's probably the odd bugs here and there still, but it's coming as a supported option as well. So that's mostly it. And the code is on GitHub, so go check it out and try it out. Any questions?
Yeah.
Yes.
I'm very curious that you have remote attestation.
Yep.
I didn't hear any detail about it, so I wanted to ask, is it possible to not be a member of the network and somehow do remote attestation and say, okay, this confidential network or whatever it is, it has system integrity. What kind of format do you use for the remote attestation structure, or some details, because I didn't see any slide about it.
Sorry,
is
so
it working?
yes, it's working. The remote attestation, so sorry, maybe something I should have made clear is we use the Open Enclave SDK, okay. And essentially at the moment, so the Open Enclave SDK supports SGX mainly, so our attestations are just SGX attestation. They're a standard SGX attestation. And Open Enclave is adding support for ARM Trust Zone coming pretty soon, so once they do, we will hopefully be multi-enclave.
The ARM Trust Zone has nothing to do with remote attestation.
They don't have a mechanism for that. Yeah, they don't have a mechanism for that now. Yeah, that's true. So, but at the moment, if you run this,
remote attestation is working.
Yes.
But and it's using the format that's Open Enclave is using.
That's right. Which is
so
the Intel.
An Open Enclave node, and I'm not part of a confidential network.
Yeah.
I can still verify.
You don't need to use an Open Enclave node. So Open Enclave provides a small utility library, but the Intel SDK does as well. Checking the remote attestation provided by an enclave. It's just a matter of getting the right certs and the right CRLs from Intel.
In the right format of the remote attestation structure.
Yeah, the format is public. I mean, it's specified in the Intel SDK documentation.
So you don't have such use case where someone wants to externally verify your network?
So we do, and so if people want to do that, so as a user, you can of course trust the network identity because it's been given to you by members and it's endorsed by members. But if you want to verify the enclaves for yourself before you connect, one of the things you can do is there's an endpoint that allows you to get a list of nodes and the attestation for each node. And you could yourself verify the attestation for each node and make sure that it's running the right version of the code against an up-to-date, Intel SGX enclave and so on. So you can do that yourself as well if you want to.
So if I would like to do that, to develop an application using the library you mentioned from
Yeah.
Open Enclave, verify externally
Yep.
confidential network without being part of it,
Yeah.
There's a way for me.
Yeah, you absolutely can do that.
To get the attestation.
Yeah, you can absolutely do that. Yeah.
False, and then verify.
Yeah, and so you'll be able to verify that basically these nodes are running with a given identity. So they'll have the public key for the pair where they hold the private key that's kept inside the enclave. You can.
The data in the quotes, like the measurements.
Yeah, sorry, what are the measurements?
The measurements that are in the attestation of the nodes.
Yes, so it's the identity of the node, the code that the node is running, and the platform details.
Yeah.
That's what SGX attestations provide to you.
Yeah. But I'll still be bounded by the SGX server, essentially, to get the attestation.
So if you do this normally, then yes, you have to talk to the Intel servers to get those certs and so on. Intel has a mechanism to delegate this. So I know that in Azure, if you use the Microsoft Cloud, for example,
Microsoft server.
Yes, you can use a Microsoft service. And you can set up your own service to do that, but you have to talk to Intel. It's probably not super easy, but it's something you could probably do.
Could we exchange contacts about that? Because I would be
Yeah.
curious.
I have business cards, and you come to me after
I want to
talking.
give opportunity to other people to ask our company.
Yeah. Okay, good.
But thanks for the answer.
Thank you. So you had Vasily? I'm sorry? How scalable is the framework? So that's a really good question. So the largest tests we've run so far were with about 20 nodes. So we run that to do performance benchmarks that we put in the initial technical reports that we published about a year ago. And this was across 2 regions. So at the moment, Azure only supports SGX hardware in East US and West Europe regions. So this is sort of 10 nodes. There's like 10 nodes one side, 9 nodes the other side. And can you scale it to a larger number of nodes? Like, we hope you can. The benefits are not super clear. So if you use Raft, if you use the CFD implementation, the only thing that more nodes lets you scale is reads. So you can scale the reads across the nodes, but the writes still have to go through a single leader. So you're making the leader busier because it has to replicate to more nodes. But if you have a read-heavy workload, it might still be a nice thing. You can also upload signature verification in cases where you have proxies. So if your commands that come in are signed, because the nodes are are verified and are part of your trusted compute base, you could have them verify the signatures before they send stuff to the primary. But it's not a whole lot you can offload to secondaries in that situation. And in PBFT, unfortunately, it's worse than that because really every operation is a write conceptually because you need to get proper consensus on it. So it's not just a leader doing things and pushing updates out. So in that case, you could scale up to a large number of nodes, but it's probably going to cost you a lot in performance. It will give you good availability, so you'll be able to lose potentially a lot of nodes, but there won't be super good benefits. So there's work ongoing, and this is slightly longer term work. It's probably not something that's going to come out this year to add sharding to CCF and to really scale out to larger volumes. At the moment, if you run CCF applications, the best benchmarks we have for applications that are written in C++ are somewhere in the vicinity of like 50, 60,000 transactions per second. So you can run like some stuff already. It's not extremely large scale, but you can run reasonably large applications across 2 data centers, geo-replicated and so on. And with sharding, we're hoping to do more. So I don't know if that answers your question, but yeah.
For the proposal, what kind of user? Is there any signature involved besides the hashing? Or to identify the identity of a user?
Okay, so the question is, if I'm a new user, do I have to sign anything? And the answer is, you don't have to. So it's standard TLS. So if you have, as a new user, you won't automatically be allowed to take part in the service unless the service is configured to be very open. Typically, it's TLS end-to-end. So what would happen is you'd have to talk to one of the members and say, I want to participate. Here's my identity. Can you add me? That member would stage a vote to add you. Then the rules of the governance would apply, and you'd get it. Now, there could be schemes where you're automatically allowed to participate because your cert has been endorsed by some identity, of course, and then the governance might decide to do that. But basically that's how the scheme works. And so once you've been added, you establish a TLS session, and you can start talking to the service. And that's good enough as far as the service is concerned. We do support client signatures to support use cases where people might decide to proxy things. So if you are a client and you want to talk to CCF, but you're not able to establish a direct TLS connection for whatever reason, you could build a command, sign it with your identity, send it to CCF, have someone else send it over to CCF. They need to be allowed to talk to CCF as well through their identity, but the command would be recorded with your signature and with your correct identity. There's a trade-off there. It's a lot slower to do that if you're trying to send a lot of transactions. But On the other hand, it means you can sort of route through anywhere you want. So that's also nice. And so if you're trying to build some workflows where you want verifiability for user transactions as well as governance transactions, maybe you would want to enforce that. So if you have some very sensitive user operations, maybe you force the users to sign, and then you store the signatures in the commands, and then people can offline verify things. Sorry, I don't know if I'm running out of time or not. No, but I see Vasily is getting closer. Do we still have time, or? Yep. One final question.
You did mention compromise in the recovery.
Yes.
So could you potentially even, because you have this trusted, you said you have the trusted members, like at the end basically, the T-shares you mentioned.
Yes.
So could you basically also use this to roll back the whole, like a whole state,
so
in kind of like a large-scale compromise? Could you explain this somehow?
Yes, so that's a good question. And so the answer is yes. So if the members could decide that they all agree that the last 20 transactions did not happen. And so this is a good thing sometimes if there's been a problem, but it could also be a bad thing because the members could be colluding. And what protection does the user have against that? And the answer is if they've kept their receipts for those transactions, they could say, I did have this receipt, it was committed at this version, and it was signed by your service. And although you truncated it post-recovery, I have proof that this was in there in the ledger. And so you still have some defense against that if the members decide to truncate things because they want to remove a sort of inconvenient rather than illegitimate operation. But yes, when the members get together, so the process, the way it actually works is you spin up a bunch of nodes, they look at all the ledgers, they verify all the entries and the signatures that are in there, and they give the members back information about which one is the longest and has still been globally committed. And then the members can decide to vote on that. They could decide to shorten the prefix for whatever reason. So signatures in the ledger, just to be clear, are signatures that are done by nodes. So they allow you to attribute the operations to a particular node. So if you know that some nodes were compromised, then this is how you can decide to truncate various things. Yep. Thank you.